I want to start by sharing a story. A visitor was observing a class of elementary students and he noticed that one particular boy was kind of hiding his work. So with a bit of encouragement, he had the child reveal that he actually completed this algorithm correctly as shown. So the visitor said, "How did you get that?" Because there was no jottings on his algorithm. And the boy said, "I can tell you, but don't tell my teacher." He said, "Sure." So the boy said, "I started with 37, added 20 and got 57, and then I added 5 more and got 62. And the teacher said, or the visitor said at least, "That's a great method. Why can't I tell your teacher?" And he said, "I won't be given a mark. I don't understand the algorithms, so I just do them in my head and write the answer down." So in this episode, I'm going to talk to you about the hows and whys of mental computation and share some powerful strategies that work right across the grades with whole numbers and even beyond. The boy in this story didn't understand a particular written algorithm, but he did have a good sense of numbers, which enabled him to develop his own powerful mental strategy. That suggests that you need to have number sense in order to be able to compute mentally. But it stands to reason, as mental computation is one of the hallmarks of number sense, that you will be developing number sense if you try and get the students to compute mentally first, ahead of using other tools such as written algorithms or even a calculator. Now this raises two questions. What is mental computation and when should mental computation be used? In short, mental computation is simply the ability to do a calculation in your head without the use of any tools, such as paper and pencils, written recordings therefore, or even calculators. Now, just as an algorithm is a written recording, well, so are number lines. So if you're using a number line to help you compute, I would not necessarily call that mental computation. You're probably just doing that to show your thinking. It is also different to mental arithmetic, which you might have heard your parents or maybe your grandparents talk about. Mental arithmetic is about speed and accuracy, whereas mental computation's often associated with efficiency and flexibility and accuracy. Mental computation is also very personal. The strategy you use may be very different to those around you. Now let's take a look at this addition example. It would not be unusual to hear all these different methods for calculating the answer from just one classroom where number sense is nurtured. Matteo, for example, he says 37 plus 29 is the same as 36 plus 30. So what's he done? He's rounded the 30, so to speak, but he's only done it by moving one from the 37. He has a good feel for numbers. Jaden, it seems to me that he likes working with multiples of 5. So he's used the nearest multiples of 5 and then added more to compensate. Aria, 37 plus 30 is 67. So she's clearly rounded the 30, or the 29 to 30, I should say, and then she's had to adjust her answer for that rounding. Elijah, he rounds both numbers. So as they're both rounded up, he's got to take something away from his answer to compensate. And Emma, she says 7 plus 9 is 16, 3 plus 2 is 5, plus the 1 is 6. So you can see what she's doing. She's doing the formal written algorithm. And she's not even talking about the 3 as being 30 and the 2 as being 20. She's simply reciting or saying the symbols themselves. Now, which of these students would you say have a good sense of number? Well, you could be forgiven for saying they all do. But when you look at Emma's strategy, you could say that it's rather inefficient, and also that maybe she lacks the flexibility or the repertoire of strategies from which to choose. Maybe she's stuck with that one strategy of the written algorithm. So then I hear you say, well, she got the right answer, so why does it matter? Well, my reply would be, it works there when you're dealing with smaller numbers. But when she gets into greater numbers or different kinds of numbers, maybe that strategy will be far too inefficient. Maybe she needs to be directed towards something that's far easier and more efficient. Now let's take a look at some nice strategies that work right across the grades. One of the first strategies that I personally learned to use when adding more than two numbers was to look for pairs that work nicely together. These are often called compatible numbers. Let's take a look at one. A movie theatre sold 165 senior tickets, 220 adult, 180 student and 35 children's tickets for a film's opening night. How many tickets were sold in total? In order in which they appear, the problem is 165 plus 220 plus 180 plus 35. That seems a little overwhelming, but when you step back a bit and take a second look, you can see that some pairs are easy to add. In this problem, 165 and 35 combine to make 200, and 220 plus 180 easily add to 400. So the problem is simplified to 400 plus 200, which is 600 tickets. And the same strategy can be applied to fractions and decimals. Let's take a look at this example involving tenths. A tourist boat needs to travel 3.2 nautical miles, 6.4, 2.6 and 4.8 nautical miles between 5 tropical islands. How many nautical miles will it travel? Here are the numbers again. 3 and 2 tenths plus 6 and 4 tenths plus 2 and 6 tenths plus 4 and 8 tenths. Can you see and add numbers that seem compatible? 4 tenths and 6 tenths makes a whole, so these two numbers easily add to 9. And 2 tenths and 8 tenths also make one a whole. So that means this pair adds to 8. So the boat travelled 17 nautical miles. There are many other powerful strategies for adding numbers mentally, and I simply can't get them all done in this episode, but they will come to you in due course. And the same can be said for multiplication, but there are a couple of multiplication strategies that I really want to show you, as I think they are often overlooked. Take a look at this problem. A garden of corn has 32 rows with 25 plants in each row. How many plants are there in total? So after you identify this as a multiplication problem, you might be tempted to multiply 32 by 100, then find 1/4 of the product, because 25 is 1/4 of 100. But you could also multiply the factors of one number to make an expression that is easier to figure out. For example, 32 is the same as 4 times 8. 25 times 4 is 100, and 100 times 8 is 800. It's not necessarily any more efficient than multiplying by 100 and dividing by 4, but some students will find it easier as it doesn't involve division. After we factorise, we are effectively using the associative property. 25 times 4 by 8 is equal to 25 by 4 times 8. The use of mathematical properties form the basis of many efficient and powerful mental strategies. For example, we can use the distributive property to solve this. We know 4/8 are 32, and if we don't know that 3/4 of 8 is 6, then we should be able to figure it out pretty easily. So the product must be the sum of those two partial products, which is 38. Before I leave you, I want to show you one more strategy, and it involves subtraction. Let's take a look. Malik was ranked 123 in world tennis. He is now ranked 58. How many places has he moved up the ranking? Subtraction is interesting because the words in the problem can often influence the strategy you use. With this particular problem, I could start with 123 and subtract 58, or I could start with 58 and count up to 123. But in both cases, the numbers are rather messy to use in my head. An alternative would be to adjust the problem to suit, and this is where the number line becomes a useful representation of the strategy. Here are my two numbers. Malik was 123. He is now at 58. This is a comparison subtraction problem, as we are trying to figure out the difference, which is represented here by this jump. Now, as long as this jump or difference remains constant, we can change the numbers to suit us better. Let's slide the jump 2 positions to the right. Now we have 125 subtract 60. That makes it more manageable to either count up from 60 or to count back from 125. Or maybe you just know double 60 is 120, so the difference is 65. Now, as I said earlier, if you're using a number line like this to help you figure out the answer, then technically I wouldn't call that mental computation. But representations are absolutely necessary to give students the mental picture of a strategy that is efficient, accurate, and flexible. Now, this is what I want you to do. 1. Remember that the use of accurate, flexible, and efficient mental strategies is a hallmark of good number sensitivities. And 2. Encourage and value the use of many strategies for different problems in your classrooms. There's no one right strategy to use. And 3. Don't just give students strategies, allow them to develop mental methods over time using hands-on and pictorial representations. And although that fell outside the realm of this episode, I think the strategy of subtraction that I gave you is certainly a good example of what I mean. And finally, if you've seen value in this episode, give me a thumbs up, share it, and subscribe today so you never miss another learning opportunity with me. See you next time.